Welcome back, everybody. This is our last video in geometry. I'm going to be flying back today, and I will see you guys tomorrow. I hope you've been learning well through this thing, but as we've been going through, I just want us to understand these learning targets, the big ideas, make sure we have a good foundational understanding of probability. Let's talk about basic probability. It's really how do we determine probability? And again, the notation looks like this. The probability of event A is equal to the number of event A. We typically think about as a favorable event, even if it's not something that we want, it's the thing that we're looking for, out of the total possible events. Okay? All right. You can apply this to lots of different situations. For example, what's the probability that I would roll a dice and roll a die and get a number that's less than 4? Or let's go with less than 3. What's the probability that a roll is less than 3 die? All right. What's the probability that a roll is less than 3? Well, there are two numbers that are less than 3 on a die, 1 and 2. So that gives us 2 chances for that event. How many possible events? There are 6. So it's 2 out of 6. Again, we can always simplify this, but it's a little bit easier to keep it like this whenever we add, subtract, multiply, or divide, because oftentimes our total possible events will be the same as we go. All right, basic probability. Can you calculate a basic probability? Give yourself a quick score on that. A 1, 2, 3, or 4, put it right up here. And for me, it's a 4. Go ahead and give yourself a score. All right, next, let's do probability rules. Let's talk about the and the or probabilities. Now, these rules occur differently based on the situation. First, let's do the or probability. Probability of event A or B. So if you've got one event or the other, that's the same thing as saying the probability of event A, then do a U, kind of a, that's called a cup, B. Okay, A or B. Both of those notations are correct. I like this one more because I like teaching statistics, and future statistics classes or probability classes, you'll be using the or symbol. It's especially prevalent in college and beyond. All right, so the probability of event A or B. Well, that's equal to the probability of event A, number of favorable events A, divided by the total, plus the probability of event B. But as we've seen before, we could double count. So that means we need to subtract out the probability of event A and B whenever both of them occur at the same time. But there's sometimes a special case, and this special case works like this. If A and B are mutually exclusive, then this result. The probability of A or B is equal to this. Just combine them, okay? Just add them, because again, I want to emphasize this subtraction here. This is because we counted twice. This gets rid of the double count. So if the events are mutually exclusive, that means there's no double counting. There's no times that event A occurs at the same time as event B. So this part becomes 0. All right? So that's our or probability. Now let's deal with our and probability. Okay, the probability of A and B, it's actually going to be equal to this. All right, the probability of A times the probability of B. But that occurs only if one special condition is met. If, okay, A and B are independent. really useful if they're not independent. Otherwise, this is how we get the probability of events A and B. The probability of event A times the probability of event B given A. All right, we would multiply B because we know that A already occurred. Okay? And those are two probability rules for the AND probabilities and the OR probabilities. Let me make a quick note because I didn't restate that here. This and this mean AND. Okay? Just like the cup means OR, means AND. All right. Finally, conditional probability. And we only introduced this. This is what our main focus will be on the lesson today. Conditional probability works like this. The probability of A given B, okay, means that we know that event B occurred, and we got to find the probability of event A. That's a calculation that we're going to need to do a little bit later, but there's going to be a special rule for conditional probability. It's actually not too hard to think through with the stuff that we're doing, but I do want you guys to see the full rule. By the way, go ahead and give yourself a score for 12B. Here. What's up? The probability rules. I got a 4. All right. Let's turn the page. We're going to go to page, I believe, 11. So let's go down here. Yep, right to the top of page 11. Now, a student committee is being formed. A student committee is being formed to decide how after-school activities will be funded. The committee members are selected at random from current club members. The frequency table shows the current club member data. So if we take a look at this frequency table, this is also called a two-way table. It goes in two directions, hence the two-way table. This way is the different places that they want to fund: drama, science, art. Over here are the different years that the students are in school: sophomores, juniors, or seniors. So one way is grade, and the other way is what they are involved in. So with that, we can go ahead and calculate certain probabilities. Let's take a look at the question up here. What is the probability that a member of the art club selected at random is a junior? Oh, so notice how this person is a member of the art club. This is a given. We know something about that. Because we know that, that gives us a bar. Okay, so we could say bar art. We know that they're an art, so what's the probability that they're a junior? And there's one special thing about them being an art. You know how basic probability is out of our total possible choices? What this does is limit the total possible choices. For possible events. Okay. I know that the total possible events are less because I know that there's a given situation. So what this is really asking is, out of all the art club members, what are the chances that that person's a junior? And we could write it like this. What's the probability that somebody's a junior given that they're in art? Okay. Let's go ahead and find out what that probability is. The first thing we're going to do is think about that art. How many people are in art altogether? Come down here, and if I take a look, art works like this. Art is here. There are 24 sophomores, 16 juniors, 18 seniors. Altogether, there are 58 people in art. So our total possible choices are 58. Now, if this was just a regular probability, my total possible choices would be everyone, and I'd have to add up all of these to get 115. So it would be out of 115. But I want to know specifically about art. So I'm limiting my total possible choices to just those in art. Now, what's the probability that one of those is a junior? If we look here at junior and art, notice where they meet up at 16. That tells us exactly what's going to go on top. This is 16 out of 58. Probability of being a junior, knowing that you're in art or knowing that somebody's in art, is going to be 16 out of 58. Now, you could plug that into a calculator and get a decimal value. As a matter of fact, we're going to do that right now. All open. Okay, so we've got 16 divided by 58. 0.27 or 0.275, let's say 6, which translates to 28% approximately. So there's a 28% chance that if somebody's in art club, they are a junior. And notice how I keep saying that if somebody's in art club, that's because this is the given. If I know they're in art club, what's the probability that they're a junior? So notice how it limits the total possible events. And this is, there's also one more way to get it. And we're going to see that here using the conditional probability formula. Conditional probability works like this. The probability of A given B is equal to the probability of A and B divided by the probability of B. Now, if I take a look at this probability of B, that's really limiting my total possible events. Remember, the bottom of our fraction is the total possible events. This part is where both of them occur. Because if I know that B occurred and I want to find out where A, both of them have to occur there. And this gives us our conditional probability formula. Now, let's go ahead and apply it to the same problem. What's the probability that somebody's a junior, knowing that they're in art? Probability of a junior knowing art. Well, what's the probability of A and B? A and B is here, 16 out of 115. Okay, 16 out of 115. Okay, and now I'm going to find out the probability of B. The probability of event B, or the probability of getting an art, that's going to be 58 out of 115. 58 out of 115. Notice that the denominators in each of these smaller fractions are the same. That'll be really useful to us in just a second, but we'll talk about it in just after we see the calculation. This becomes, because it's a complex fraction, 16 out of 115 times 115 out of 58. Notice what cancels out here. The 115 and the 115 in the numerator and denominator cancel out, and that produces 16 out of 58. These are the exact same probabilities. Now, what doing this does is allows us to see those probabilities, but it requires a little complex fractions, and most students have trouble with that. There's one other way for me to kind of show you this, and I just want you to kind of consider it as well. Technically, this is not a correct way to write it, but you'll see what I mean. Okay? The way to do this is to think of the numbers of A and B. And we're going to divide this by the numbers of event B. Okay? For our purposes, this will be really useful because we don't have to multiply and cancel out the denominator of those fractions. And let's take a look at how this works. If I were to think the probability of art junior given art, well, I just want to think, how many people are juniors and in art? If I look over here, there are 16. It's in the purple. So I know that there are 16. And how many are just in art? Well, over here, that's 58. 58. So this is one more way that you can think of it. Technically, this way, by thinking of just the numbers, isn't really correct in a mathematical sense, but it is a useful way to think through a problem. Now, from now on, you have all you need to know to be able to solve lots of these problems. We're going to talk about one more thing in the lesson, but for the most part, you can go on and work on these problems. You have try it 1, try it 2, and example 1 and example 2, example 3, example 4. All of these you can work on, and I expect you to be done with it by the end of the period. Let's go ahead and answer a few of these try it problems. Go ahead and do this one by yourself. And again, if you want to keep going, you can. And I'll answer it in just a second. Put a pause on the video. Right. Let's go ahead and discuss it. What's the probability that somebody is a sophomore knowing that they like drama? Yeah, we know all sophomores like drama, right? That's a little bit of teacher humor. All right, so let's think about this. We can think about it in one of the 3 different ways that I showed you. I prefer to think about it this way. The probability of them being in art, and think about the total number of art, and the junior way. So I'm going to do that one just because it's the most efficient, and that's most of the time how people think about it. All right, how many people are in drama? 17. And of those 17 people, how many like or are sophomores? 3. So the probability here is 3 out of 17. Right. What's the probability that a sophomore is a member of drama club? Ooh, let's go the other way. What's the probability that somebody's in drama knowing that they're a sophomore? Notice how this is a backwards thing. Well, let's go ahead and find out. Out of all the sophomores, there are 36. And of those, how many are in drama? 3. Notice 36 is the end of the row for sophomores, and 3 right there. So 3 out of 36. Now take a look at both of those. Are these probabilities the same? No, because we have different conditions. And that's why this is called conditional probability. This is our condition, the given thing, and notice how the condition's different each time. So it changes our total possible choices. Okay, so let's go ahead and make a note of that right here. Oh, and that's because the conditions in the conditional probability are different. So usually will not be equal. It'll only be rare times whenever, depending on different conditions, that they are equal. All right, let's talk about this. And this is the last thing I'm going to teach you. It's going over our 4th learning target, independence. We talked about the results if things are independent. It makes things easy to calculate. Remember, the probability of A and B, you just multiply them. Real easy to do. But making sure things are independent so we can actually use them, that's the difficult part. So here's a table of vehicles in a parking garage one afternoon. A vehicle in the garage was selected at random. Let B represent the vehicle that's black, and V represent that the vehicle's a van. Are the events B and V independent or dependent? Technically, if you take a look at that dependent, we would actually say not independent. We'll pick the highlighter there. Or not independent. Now, the reason that we don't call it dependent is because there's different variations on what dependent means. Dependent could mean direct dependence. It could mean indirect dependence. It could be several different types of dependence. So we usually don't just call them dependent if they're not independent. All right, and in order to test if things are independent, this is something I mentioned earlier, we want to see if they influence each other. And that's what we do here. Notice this statement. Over here is just the probability of event B. And that means the chance of being black, of the car being black. Okay, and what's the probability of the car being black knowing that it's a van? Now, if being a van doesn't influence the color, then these probabilities should be the same. If knowing that it's a van does change the probability of it being a black vehicle, that means that this is not independent, that they do have some sort of relationship in the same way that you would be not independent from your parents just yet. All right, so let's take a look at the events, the event B. If we take a look, black, there are 13 out of 22. So let's go ahead and write that down. 13 out of 22. But what's the probability of black knowing that it's a van? So if I take a look over here, black is 3 in the van category out of all the vans, which are 3. So this is 3 out of 3. Is 3 out of 3 the same thing as 13 out of 22? And the answer is no, they are not equal. Well, let's check the other way. Okay, what about, does black, the color of the car, influence if the car is a van or not? Let's go ahead and check that. What's the probability of picking a van? Well, that probability is 3, because there are 3 vans out of 22 altogether. So we should have a probability that's just like that. What's the probability of it being a van knowing that it's black? Well, I'm looking at this. We know that there are 3 vans that are black out of all 13 black vehicles. So that's 3 out of 13. Are these two equal? And the answer here is no. And this leads us to a conclusion for this problem specifically, that these two events are not independent, but the reason is because van influences black and black influences van. All right, so that's what we're going to write down for our conclusion. And van are not independent. Because no vehicle is a van changes the probability of it being black. Okay. We only want to check one, but in order to prove that two things are independent, both would have to be true. Okay? For them to be independent, the probability of black given van has to be equal to the probability of black. In other words, the probability or the chance of it being a van won't influence the probability of it being black, and the probability of van given black has to be equal to the probability of it being a van. In other words, knowing that it's a black color doesn't change the probability that it's a van. Both of those have to be true for those events to be independent. And that is our test for independence. All right, go on to the next page, and I actually want you to try out, see if they're independent. And the way that you see if they're independent is you check this. Is the probability of red and C, red given C, equal to the probability of red? Okay, that shows that C does not affect R, or the fact that it's a car does not affect that it's red. But we also need the other one. Is the probability of C given red equal to the probability of C? Knowing that it's red, does that change the probability of it being a car? Go ahead and try and calculate that one by doing both of those and come to a conclusion afterwards. Be like, oh, they are equal, so maybe they are independent. Or, oh, they're not equal, so they're not independent. With the next few problems, you can continue working on those, finish up the class, and I will talk to you about this tomorrow. This one's a little harder to kind of think about. It's a little bit of an advanced problem here. So go ahead and think about that. And with example number 4, we have a similar type of advanced problem. And the reason that it's a little bit more advanced is these are already dealing with percentages. So one of the things that you could do with these percentages is you can convert them to decimals and work things out the exact same way we've done before, 0.46. Okay, so go ahead and do that, and I will talk to you about this tomorrow when I get into class. But you've got 2 more problems to work on, 2 more sets of problems to work on, I should say. Example 3, try it 3. Example 4, try it 4. With the idea of independence, one of the things you just need to do is practice it. This is not something that you understand without practice. I've never met a student who understood it without doing any practice at all. Hope you guys have a wonderful day. This video might be a little bit longer, but it's my last one. Bye.